All right, hi everybody. Welcome to the second lecture for Math 6310, Chaos and Fractal Dynamic Systems. We're going to continue on from the last lecture. Let me take a minute and review some of those things. Now, first of all, we know and we said that chaos is bounded instability. And we'll get a little bit more into what that means as we begin to talk about some of the properties, some of the characteristics of chaotic dynamics. And dynamics just means things that are in motion. And then we said that there are some uses in technology. Went over one briefly. I invite you to do some research on that yourself. We talked about this space probe that was sent out to intersect a comet, and they took advantage of the inherent unstable, chaotic motion that was created by this three-body problem between the Earth, the Moon, and the actual probe itself. Created unstable trajectories that they could use to send this where they wanted with a minimal amount of energy being the fuel. And that was the benefit that came out of this. We also said that there were analogs in nature. There's examples in nature. We'll probably show more of those as times go by. As we talked about fractals, fractals are objects of fractional dimension, and we will show a little bit of an example of that as we go forward. And finally, we say fractal are generated by mathematics. There are some examples. I think we showed one of the Mandelbrot set. There are more, and we will get into some of that. And then you can also see fractals in nature. So it's not like they just live in this mystical world of mathematics, but they are out there in nature, and you can, if you look around, you will see them every day. All right, so what are some conditions for chaos or for chaotic dynamics to occur? Well, and if you think about it from a mathematical standpoint, nonlinearity is one of these conditions, but you also need a feedback mechanism, meaning that the output, and let's just say that this is just some system and it has an output, and let's say that the input is X, the output is Y. There needs to be some sort of feedback that some part of Y, some measure, alpha is just some sort of constant, for example, that feeds back into X along with, which is the input in the system. So you need some sort of feedback. Also, now if you think about it kind of physically, I like to think of this as stretching and folded. Think about kneading dough, for example. You roll it, you pull it, you stretch it, then you bring it back. You may even want to try this where you take a little bit of dough, say like this, and it's some piece like that, and put a dot of food coloring or something in it, and then begin to knead it. Well, you're going to stretch it, perhaps, right? Then you're going to fold it back onto itself and just keep doing that. And if you keep doing that, you'll begin to see that the color gets spread out, perhaps in striations, perhaps in other pieces, but you'll see it get spread out and mixed within the dough. And you would not be able to predict, say after 100 of these iterations, you would not be able to predict the exact position of all of the colors within the dough after you're done. But it's not like this is some infinite amount of dough, nor are you making an infinite number of moves. And if everything has some state, right, this dot could be measured in some position X, Y, and Z initially. So you know the beginning state, you could measure it. You know what you do for how many iterations, but yet you still could not predict with precision where the colors end up. And I invite you to do it. Maybe take your camera and videotape it, right? Take some dough, and if you want to do that, and it's flour and water, right? Put a dot of food coloring in it, and then start kneading it. And then see what happens. I invite you to do that. All right, so let's go back to the idea of these conditions. So we said nonlinearity is one of them, right? But in order to know what nonlinearity actually means, let's figure out what linearity means. Okay, so I'm going to write down one of the simplest linear equations of a single variable. And let's say that f of x equals mx plus b. Now, many of you will recognize this as the equation of a line. So here's x, here's f of x, and let's just draw a line like this. Straight line, it has a slope, that's what m is, and it has a intersection with the what we would call the y-axis. So let's just say y equals f of x. That point at which it intersects is b. Okay, so that's the equation of a line. Now, what's linear about this? Well, the effect of the function on the variable x is the variable that changes, right? This has to be of order 1. Okay, so x is of order 1, meaning that x equals x to the first power. Anything other than that, and x is not linear in that equation. Now, let me modify that to say plus and minus. Okay? And that's a linear expression. Now, if, x is, say, to the second squared, then that's no longer linear. If x is to the, let's say, 0.5, that actually means x to the 1/2, which means this is 1 over square root of x. And that also is nonlinear. Okay, so linear equations, the order of x has to be plus or minus 1, or 0. I mean, that's a simple case. If it's 0, then if x to the 0 is equal to 1, then of course that would just be a constant straight line of some sort, like that, which would still be linear, but it doesn't really vary with x. Okay, so this equation is linear with respect to x. Now let's look at something. For example, I want to introduce this notion that if you want to find the change, and if you had calculus, then this will be simple to you. If you don't, then just think of it as a change, right? First of all, let's just say the change in f of x with respect to the change in x. Now, and in the limit, this becomes what we call df dx, and that's a derivative. Of x, which measures the change. What is the change of f with respect to x? Let me write it properly. The derivative of f of x with respect to x. That's what that is. Now, so if you go back to the expression we had, this is saying, let's take this line again. How is this changing with respect to x? So in this case, df dx is, and if you know your equation, your derivatives, remember the equation is f of x equals mx plus b. The derivative of this is just m. So, because x is the only thing changing, but it's changing by m. That m value, that slope of the line. For example, think about you walking up a hill, right? Sorry about my drawing, but let's just say this is you walking up a hill. And the hill has a slope m. Well, the greater that m, the harder it is to go up the hill. And what happens if that happens to be negative? Well, the line is that way, and you're going downhill. Okay, so if you take a linear equation, it then is has a simple relationship, a constant value when you take the first derivative. That's another way you can tell if you have a linear equation. Now, as engineers, we like linear things because they're easier to work with. They're easier to solve. They're easier to design. And most engineering systems start off trying to be linear. But we begin to realize that the interesting stuff lives in nonlinearity. And so we then wanted to go further. But before we go into nonlinearity, I want to go to two variables. So now let's say that f of x and y is equal to ax plus by plus c. Now, even though that has two variables in it, x and y, they vary, it's still a linear expression. And I'm going to do this. You will pick up on it. But if I said, how does this expression vary with respect to x? Now, if you notice, the D I drew is a little bit different. This is called a partial derivative. How it changes with respect to x would be the same thing, but with respect to x, y is a constant. So this would only be a, because a is a constant with x, but this is a constant, so its derivative is 0, and of course the derivative of the constant c is 0. So this is just a. And by the same token, the partial derivative with respect to y is also a constant, but what do you think that is? Well, again, this varies as a constant with respect to y. B is not, but it's linear, so you get the constant b, and that's 0 as well. So these are the two derivatives. So the change, again, with respect to either variable is a constant, so therefore this is linear. Now, I'm going to, in next homework problem, we'll provide you a series of equations, and I'm going to ask you whether that is a linear, nonlinear, is it variable with one variable, two variables, or three, or whatever. And you'll just answer those questions. That'll be in your next homework, and you could show, I want you to show reasons why they would be linear or not linear. Now, let's take a look at another example, because sometimes you want to know something about two things that are happening at the same time, two or more things, and we'll just use two at this time, that are happening at the same time, and there's some relationship that you're trying to figure out. So let's set up a problem. Let's just say that we have, again, we have two lines, and we're going to use y equals mx plus b, right? So this is y. And we have two lines. And one line looks like this, another line looks like that. And we're going to want to know where these lines intersect. And that is some value, we call that x I for intersection, right? We want to know what that value is. Okay, so we have the first equation, we call it y1 is equal to m1 x, because it's the same x, plus b1. Okay, so that's 1. And we have y2 is equal to m1, I'm sorry, that's not right, m2 x plus b2. All right, so this is a system of equations. And what we also know is that at this point where they intersect, this is called y1. Now, I'm not going to put, I'm sorry, not y1, yi for intersection. Now, I'm not going to put numbers here per se, because I like to work more with variables than numbers, because once you get a solution, then you can just plug it in for anything, right? one of the things we can kind of tell, just the way I drew it, is that B1 here is positive, and B2 here, because this is Y2, and this is Y1. And so B2 is negative in the way I drew it. Now, that may not necessarily be for all cases. This is just in the case that I physically drew for you. Now, but the slopes as drawn, M2 is positive, and looks like M1 is positive, meaning that they are positive slopes. One's not running downhill. Now, what we're trying to find, though, is the situation where Y1 equals Y2. And what we know from this is what? We know that they're going to be equal to each other at this point, x1. I'm sorry, xi. Let me get that all straight. At this point, xi is going to be equal to each other and is going to be equal to yi. So we know then, let's say that as an equation. We know that y1 equals m1x sub I plus b1 equals y2, which is equal to m2x sub I plus b2, which is equal again to y sub I. Okay. So you could do this a couple of different ways, but the best thing to do is to, because what you're trying to do is figure out what M1, M and M2 need to be. No, let me, that's not what you want to find. You're going to assume that you know what those are. What you really want to find out is what is xi equal to in order for this to be true. What is xi and yi equal to in order for this to be true? So you could just start off with this, and you could say m1xi plus b1 is equal to yi, right? And then you could just solve for x1 with respect to everything else. So this would be, if you follow this, move the b1 over and then divide by m1. So xi is equal to yi minus b1 over m1. Okay? So we got that. Now we need to know what is yi. Well, we can now use this one. Let me do something right quick. Let me just extend this. I'm going to get rid of all this stuff. Create some room. All right. So you should be able to see this still over here. So then we'll say yi, we know, is equal to m2xi plus b2. But from here, we know that xi is equal to y I minus b1 over m1. So we could take this and plug it into there, which would say yi equals m2 yi minus b1 over m1 plus b2. Well, what does that do for us? Well, that allows us then to have this now all in respect to yi. So, and then we can solve for it. So just to expand it out, you got yi equals m2 over m1 times yi minus m2 over m1 times b1 plus, no, that's not a I, that's a 1, plus b2. All right? And can move this over. yi times 1 minus m2 over m1 equals m2 over m1, b1 plus b2, and then you can divide by that and you'll get what yi is equal to. Now, I just went through all that. This is all just an example of setting up an equation with an expression to answer a question. So if you go back to this, we're answering the question, if you got two lines, where do they intersect? And if they intersect. So these will give you the general expression. Here's your, for where y1, and here's yi, and this is xi, and that's where they intersect. So, and if you can, now there would be situations where it wouldn't work. As you can see, for example, if m is equal to 0, you wouldn't have any real solution to it. Same thing for other examples you could think of. But that's just an example with a linear equation. Now, I wanted to just do that because now I want to talk about discrete time maps, which again can just be an expression, but usually we're talking about something that is a mapping, which would be points. So let's look at, let's call this x of n and x of n plus 1. So you got this system that you put in x n, and then you get out the next step. So this tells you if you have a point here, call it x1, and then the other point, x2, this is x2. Then as you, now x2, let's just say this is x2, that gives you, say, x3. And as you go on in time, you'll build up a shape for this. So you still can have x of n plus 1 equals f of xn. So there's some sort of expression. So, but again, we were talking about linear, but the interesting things are nonlinear equations. Now, I'm going to give you an example of a nonlinear equation a little bit later. But let's now go into this idea of differential equations. So we brought this up before, and we said, here's f of x is equal to some function of x, and df of dx sometimes could be called f prime. Sometimes you see it called f dot, because it doesn't necessarily have to be an x. This could be df with respect to time, so the change. But derivatives are about changes, okay? And sometimes you just see this as y, right? Y dot, or y prime, or even x dot or x prime. So whenever you see that, usually a differential equation is at hand. And the other thing I'll say about that is you can have, this is what's called a first derivative. This is how things change. How do things change with respect to x, with respect to y, with respect to t, whatever? How do things change? The first time, the first change. Remember the slope. What is the first change? But suppose the slope was changing too. Well, then you would have to say, what is the change of the change? And that would be a second derivative. So f double prime would be d2f dx, the second one, which is the derivative of x of the derivative of df dx. That's the second derivative. Now, in the case we use for, remember, f of x equals mx plus b. Well, the first derivative is going to be equal to m, but the second derivative is equal to 0, because that's a constant. So the slope doesn't change anymore. And that tells you a lot about the system itself. So differential, now this is the differential. Now let's, and I want to do this too. I want to just say a little bit more about this. So let's do what we did before and create some more space for ourselves. I'll just erase this the old-fashioned way. All right. So a differential equation is one that has a differential in it. So if I said d y dx plus y equals 0, that is a differential equation, which I could also write as y prime plus y equals 0. That's a differential equation, which says the change in y with respect to x plus y is equal to 0. So you might just intuitively say that if y was equal to the minus dy dx, then that would be a solution, which kind of makes sense if you just do the algebra on that. But what types of expressions are where you can take y and it's equal to the negative of itself. Or another, maybe even simpler one would be dy dx minus y equals 0, which would say that y is equal to dy dx. What situation is that? It's not as simple as you might think. Because if I said, well, let's just use a constant, well, if a constant dy dx, if y was a constant, then that would be 0. So that's not the same. And even if I said, y was equal to x, then y prime is equal to 1, and that's not equal. So there's not a simple solution to that. There are some expressions that we could find out about that would actually solve it, but I'm not going to go into that now. This is just an example of a linear differential equation. Now, I did something here that also I wanted to go into, and that is you could have systems of differential equations. This would be y prime plus y equals 0 and y prime minus y equals 0. And if you wanted to solve and find a solution, this would be a two-system expression that you might want to try to find a solution for. But as complex as this may look, this is still a linear system of equations that has solutions that you could end up finding, and they would be interesting, but not terribly interesting. So, I want to talk about nonlinear equations. So, let's start off with one of the simplest ones, and that is f x is equal to ax squared plus bx plus c. Now, you may recognize this as an equation of a parabola. Oftentimes like this. But it could be flipped over if it's negative. It could have different places where this intersects, where it is, where that hump resides. So let's find out where that. Now, what is it about this hump? This hump says that right there, see this, if you remember what I was saying about the line, the slope is actually changing here. With respect to x. And I'll prove that because the slope is df dx. That is identically, mathematically, that is the slope. Well, what is that? Well, I'm just going to solve this. You can go back and review your differential equations if you want to. This is not going to be a calculus class. I'm not going to have you solving a bunch of differential equations, but I want you to see that this is going to be 2ax plus b. This is 2ax. You bring that exponent down and leave that, subtract one of the powers, and that's what you get here. This is just the same thing, but you see only the constant is left, and that one is 0. So this is the solution. Now, as you can see, there's still a x. Now, what we know right here is that this slope is equal to 0. So, and in this type of expression, that is the only place where it's equal to 0. So we could solve 2ax plus b equals 0. And if we solve that, we'll see that, and let's call this x of 0. So x of 0. So we'll solve this for x of 0 is equal to minus b over 2a. That is where this hump resides on this expression. And it's dependent upon the two constants. So, all right, so you're going to want to remember that. We may ask you to show that for one of the expressions that we'll be playing around with. All right, so now I want to go back to this notion of this system of differential equations, because if you had one that you wanted to look at, you could look at an expression and say, I want to look at y and y prime versus each other and see what it does. So if I had a situation like, let's just say y prime equals 2y, okay, that's a legitimate differential equation. Then this would just be, you just plug it in. And what happens when, let's just take different examples. 1, 2, 3, 4, 5. Well, let's just say 2, 4, 6, 8. Well, when y is equal to 1, 2, 3, 4, 5, y prime is equal to 2, 4, 6, 8, 10. And you could plot this, and as you can see, it's just a line, which again is not terribly interesting because this is a nonlinear, this is a linear expression, not terribly interesting, but it is the notion of a state space. What does a state space mean? It means what is the state of the system at any given moment of everything that you can know. What is everything that you can know about this system? So I want to show you some examples of some interesting chaotic systems. And this, we'll end here with these two examples. I want to do a little bit more, but I'll stop here. I don't want to overwhelm you with stuff. You can read about a lot of this. But here's an example of the Lorentz system. Now, interestingly enough, I'll give you a quick backstory. Read about it in the book. Edward Lorenz was a meteorologist who's trying to figure out how to predict the weather. And he had some mathematical expressions that he had pared down from fluid dynamics equations, Navier-Stokes, I believe. And these are the equations right here. And he began to, at the time, this was in the 50s, they didn't have our fancy computers, so he was calculating by hand, and, he's calculating, x1, y1, z1, then x2, y2, Z2, so on and so forth. And he had started plotting this, again, by hand, and then he stopped. And stopped at, let's say, X, 1,000, Y 1,000, Z 1,000. That's where he stopped calculating for the day, went home. Came back in the morning, started back up. Instead of starting up right at 1001, he said, let me make sure I'm going to go back and I'm going to start probably, let's just say, at X of 820 and so on. And start calculating again, plug the numbers in. Well, he did that and found, and he made a slight error in his decimal place at that point. He made a slight error. Well, he began to see that the solutions diverged a little bit. I won't try to mess this drawing up. But they weren't, when he got back to 1,000, his value was not the same as what he had calculated before. And while he noted, oh, I made an error, he said, why would it be so wildly different when it was just a slight error, say of a hundredth of a decimal place, but it created this big error when he got to it. And so, again, I'm only recounting the story anecdotally. It's in the Gleich book. You should read that. But this is what came out of this nonlinear expression as we began to look at it more closely with our computers and everything. So this is one. It's called the Lorenz system. Now, here's another, and this is an example in engineering. This is an oscillator, and it's supposed to generate nice sinusoidal oscillations that you can use in order to, let's just say it's the current with respect to L of time, and you have the voltage of E, which is this. So the current in L is this. This is IL, current flowing here. VE, which is right here, and VC, which is right here. Those are what you're measuring. And you want nice sinusoidal oscillations to use for various electronic examples. Well, this is a nonlinear equation. Why is it nonlinear? It's subtle because you don't see it in here per se, but this is where the nonlinearity comes in. This is an exponential function. It's stuck right here. Everywhere else, this is a linear equation, but you need the nonlinearity in order, which is what this what this transistor does. You need that in order to create nonlinear stuff, interesting stuff. You need nonlinearity to get these variations because this is otherwise a linear circuit. But with that little bit of nonlinearity, with the right values, you can create something that looks like this. Okay. So we'll talk some more about all of this. I want you to read about it. I want you to do some research. Go on Google, go on various links, and just look at these things. Look at what they do. Another thing we're going to do is I'm going to introduce MATLAB to you, let you play around with the expressions. I'm not going to have you figure out how to write these equations in MATLAB. I'll do them for you, but give you where you can play with different values and get output. That's the way I'm going to do it. So it should be interesting and a little bit fun and not, I'm not trying to teach you coding. But here is the Colpitts oscillator in certain situations, all right? Now, let me end by doing this because I didn't quite explain this right the last time. I wanted to, I'll use this color. This is the Sierpinski triangle. How do you actually generate this? So you start off, it's by you're taking something away. So what you see that's going to be in gray is, oh, that's not a great color. Let me do it in black. So just think of the black as what's being extracted from this. All right, so you're going to cut out a section here. So now you have 3 triangles. Okay, and you're just going to keep repeating this process. So that's kind of level 1. And then I'm going to do it again on each one. Take that away. Take that away. Take that away. And now you have 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles where you had 3 before. So when you do the first one, well, let's start 0. You have 1 triangle. Then you have 3. First iteration. Second iteration, you have 9, and you probably can see how this goes. So what you see in red, it's what's left. And you keep doing this. You keep doing this. And as you could probably imagine, now you have, instead of 9, you're going to have 27. And you probably can see that if you take the iteration number, call that n, then the number of that you'll get is going to be 3 to the n. So when that's 0, of course, that's 1. 3 to the 0 is 1, but 1 gives you 3, and so on and so forth. That's how many you have. So at some large number, capital N, you get 3 to the capital N. That could be 1,000, that could be 1,000,000. You get that many, but the volume and that is actually reducing, or the area. Let's say the area is actually getting smaller and smaller. But do you ultimately go away and it becomes 0, or is there some number? Because as you continue to take more and more of this away, what do you have left? That's the question. One more I want to show you, and this is an easier one, and this is called the Cantor set, and it's called the middle thirds, simply because if you take this initial line like this, and then take out the third, this becomes this and this. Now you take out the third again on each one of these, and it becomes this, 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 and this, and you just keep doing that. This and this, this and this, this and this, this and this. Okay? And then you have a number. So this is how many you have. That's 1. That gives you 1, 2, 3, 4. That's 4. And then, I'm sorry. This is 2. I'm counting the little parentheses, and I shouldn't have. That's 2. You got 4, 8. And so you can see in this case, for the iteration number, say 0, 1, 2, and so forth, the number of pieces, elements, whatever you want to call it, that is going to be 1, 2, and 4. So you see that then is just equal to 2 to the n. That's how many you get. And the next time we talk, we're gonna talk about dimension, and then I'm gonna tie this together. What is fractals and chaotic oscillations? What do they have in common? We're gonna look at a map, a chaotic map, two-dimensional map, and start to see where those connections start to tie together. So, all right. Now, we're going to have this coming lecture week. We'll have our quick question and answer section. So, I urge you to come with many questions. We can walk through it together. All right. So, what did we talk about? Well, we talked about linear equations. We talked about differential equations. We showed some strange attractors, and that's what they were. Did I spell that right? There's a C. Strange attractors. But they were the state space for these chaotic oscillations. And then we talked about a little bit about fractals. So we're going to calculate dimension. We're going to look at nonlinear maps next time. Okay? All right. Hang on. I know I threw a lot at you today. We'll work it through. We'll talk it through. I'll give you some homeworks that helps you kind of understand a little bit about what we said. And we'll just keep on forging on. So take care.